By Monika Středulová and Jean Ennis.
So good afternoon, everyone. Thank you for the introduction. My name is Monika Středulová. I come from the Czech Republic, from Brno University of Technology, Faculty of Civil Engineering and the Institute of Structural Mechanics. In the next 10 to 15 minutes, I'm going to talk about the friction effects in uniaxial compression of concrete cylinders. The work has been done in cooperation with my supervisor, Associate Professor Eliáš. Now, just for a brief introduction, strength of concrete in compression is one of the most important characteristics when it comes to designing concrete structure. If a structural engineer needs to model an existing structure and he has no information about the material, then usually the strength of the compressive strength of the material is obtained experimentally by uniaxial compression. You can see the experimental setting there. It is usually done from drill core cylinders subjected to uniaxial compression by two platens. Now, often these platens are made out of steel. As a result, there exists friction on the interface between the concrete specimen and the steel platens. Now, this friction plays a very important role in the failure mechanism of the specimens, because a zone of confined compression occurs close on the interface. You can see a schematic picture on the right. Now, if we take a specimen of a larger slenderness ratio, such as the one on the left here, the zone of confined compression is depicted by the pink color. And this specimen is going to fail by splitting cracks. The zone of confined compression doesn't play an important role. On the other hand, if you take a look on the low slenderness ratio specimen on the right, you can see that the zone of confined compression takes much larger portion of the material. And as a result, this changes the mechanism of failure, and the final force which is needed for the specimen to actually fail can be up to 2.5 times higher than for that of the first specimen. So, and this was in fact the motivation for the work I'm going to talk about in more detail. It was to investigate this effect of friction, to which extent it affects the compressive strength obtained from the experimental testing. Basically, we did we performed some experiments, and subsequently we modeled these experiments by a very specific discrete model of concrete, about which I'm going to talk about just now. So the model we used, it's called lattice discrete particle model, was originally developed by Professor Kusatis of Northwestern University, who is also a collaborator of Professor Eliáš, my supervisor. It is a mesoscale model which was developed specifically for concrete. This model explicitly considers individual particles, so it actually considers the real physical behavior, the interaction of these particles. Now, as a result, the model is able to show the real mechanism of failure and the real mechanism of the behavior of the material. So you can see that we are able to, the model is able to show such scenarios as diffuse cracking, as the picture in the middle, or localized cracking, and so on. So the model can be used for a full range of loading scenarios when it comes to concrete. You can see it has been extensively validated, and you can see just two examples. The first one is a projectile impact simulation. in reinforced concrete, and the example on the right is a tensile splitting test. And as I said, there are two main advantages to the model. The first one is that it is really able to model the complete range of concrete behavior because it actually represents the physical mechanism. And the other advantage is that it actually considers the physical parameters such as granulometric curve and water-to-solute ratio and so on. So as a result, it should be much easier to calibrate in practice. Now, the way we introduced friction into the simulation is that obviously we wanted friction to affect only the base particles which are in contact, let's say in reality, with the steel plate. So these particles are free at the beginning. Subsequently, as the compressive force increases, there is a lateral force acting on the particles which increases linearly at the beginning and subsequently changes into a constant lateral force. Now this linear increase is quite important because in reality the surface of concrete specimen is never smooth, so in the first phase there is always an increase in the force, let's say. Now let's take a look at the experimental data. You can see dimensions of the concrete specimen in the table. I won't read it here, I don't think it's necessary. I think the most important line is the slenderness ratios, which we tested. It was from 0.5 up to specimens of slenderness ratio 2.5. We tested 3 specimens per each slenderness ratio. You can see results of the experimental testing in the picture over here. That is the tallest slenderness ratio. Now let's take a look at the results of the simulation. In the graph you can see on the x-axis there is a slenderness ratio starting at 0.5 up to 2.5. And on the y-axis there is the maximum force which was needed for the collapse of the specimen, normalized with respect to the force obtained for the tallest specimen. Now, as you can see, for the tallest specimens there is not much of a difference in the resulting force. It is all in the limit, let's say, of the standard deviation. However, as we go lower to the slenderness ratio of 1.0 and even 0.5, the force radically increases up to 2.3 times the force which was needed here. So in this, we try to replicate the results with our model. So in the first phase, you can see the cases which we ran the simulations for, the slenderness ratios that we tested. We tested 5 geometries per each slenderness ratio. Now in the first phase, we used 2 different boundary conditions just to see how the model behaves in the extreme cases. The first case was that the basis particles, the particles adjacent to the steel platens, are fixed, so there is full friction, no lateral movement is allowed. And the other case was that the particles are free, so they can move freely, there is no lateral constraint. Here you can see just a graphic representation from the model, which shows the crack opening which was obtained by the model. Now let's see the results. In red there are the experimental results which I already showed before, and then there are curves for both cases, the full friction and the no friction case. You can see that the free boundary condition actually corresponds to the fact that there is no confined compression zone, and so the final force is not much affected by the slenderness ratio. However, in the case of the fixed boundary condition, it is complete opposite. You can see that it changes drastically even for slenderness ratio of 1.0. You can also see that the experimental results are somewhere in between these two cases. So we presume that there is indeed the simulations. We presume that there is indeed some friction happening and that has this effect. So next we proceeded to simulations which actually included the friction effects with the frictional coefficient. So in the graph you can see just the bounds which I showed before for the free simulation and for the fixed simulation. The experimental results are always in red. It's still for different slenderness ratio. So first we tested friction coefficient of 0.4. You can see up to slenderness ratio of approximately 1.1. It is quite similar to the fixed boundary conditions, and then it changes slowly, slightly lower. On the other hand, for extremely small friction coefficient, you can see that the results are similar to the free simulation. Not completely the same, but it approaches. And finally, there's a value of 0.2, which, as you can see, approaches the real experimental solution. And the last value of friction coefficient, 0.1, that we obtained a really nice correlation with the experimental results. So yeah, so we can conclude that the model is able to model this behavior really well, in fact, and actually the main focus of my work is the model itself. This research into frictional effects is more of a preliminary work. So thank you for your attention. If you have any question, I will be happy to answer.
Yeah, I have a question. What happens to slender radius 0.5?
Yes, well.
I assume it did not converge or explode.
Yes, yeah, here are the results for only starting at 1.0. For 0.5, well, we did get results, but looking at the low displacement curve from the simulations, we weren't actually convinced that the data are correct. Because it seems like, because the specimens were really small. Actually, it was 5 centimeters diameter and 2.5 centimeter tall, and from the results it looked like the confined compression zone actually acts really strongly if the particles are fixed, and it looked like well, we weren't convinced by the results, but actually the immediate work after the conference is the implementation of improved of improved material models. So we are hoping to revisit the simulations with the different.
And how many particles did you use for your virtual model?
Well, it depends on the ratio. Obviously, I think it ranged from 500, let's say, to 3,000, maybe, depending on the geometry as well, because each geometry is generated randomly, and so yeah, each geometry has different number of particles.
Yeah. And the last question is, I am not an experimentalist, so I have no idea about that. But did you try to basically pull some concrete specimen over steel to measure the friction between them and compare it with the found value?
I'm sorry, I'm not sure I understand your question.
Yeah, I mean, you could basically measure the friction coefficient.
Coefficient friction between the plates and
no.
the spacemen.
No.
Yeah, it would be interesting if it is 0.1.
Yeah, thank you for the suggestion.
Yes.
The specimens you used were of constant diameter and increasing length.
Yes.
Did you consider perhaps the influence of size effect? Because if I see your model for zero friction provides almost constant results, which means that there is no size effect.
Yes, well, the importance of size effect. Yeah, well, actually,
Explain some results close to very small slender nature besides friction, I think.
yes. So, yeah. Okay. Thank you.
So normally in this case, even from numerical point of view, probably should be some size effect related to the Weibull distribution. Strange, there is nothing. Can I ask a question? Of course, normally in all the code, we have to use 2.0 as a slenderness. And when you pass to 1.0, of course, you have to increase. Have you checked from the codes if the results you obtain are consistent with the codes or not?
Oh, to be honest, I did, but only at the very beginning, and I'm afraid I don't. I cannot.
Because this is the most important test that we did, particularly in this structure. So.
Yeah, I'm sorry, I cannot.
I work a lot on this geometry and size effects in particular, considering of course the friction action, but I use some device to avoid friction.
Yeah, that's also possible. Yeah, to use Teflon to.
I use tubes, Teflon,
to
the oil
okay.
in between. It was impressive because the problem was that the specimen.
Oh yeah,
move around because it was no friction at all.
Increasing
friction.
It's difficult to center into the.
No, it was simple. The problem was completely avoid the friction. Strange. Thank you very much.